Thanks for coming to the ME seminar series. Today, it is our great pleasure for inviting Professor Peter Hosemann to deliver today's talk. And Professor Hosemann is a world-leading scientist in the areas of micro-scale mechanical testing, materials corrosion, and degradation under extreme environments such as irradiation. And he currently holds the ESQ Chair Professorship at the College of Engineering at UC Berkeley, and he's also the current Nuclear Engineering Department Chair there at Berkeley. So Professor Hosemann received his PhD in material science from Universität Leoben. I learned it yesterday, hope I didn't do it too bad. Austria in 2008. And after that, he worked at Los Alamos National Lab shortly, and then joined UC Berkeley faculty in 2010. So Professor Hosemann has already authored more than 200 peer-reviewed publications, and he has also received many recognitions from the community. For example, in 2014, he won the Best Reviewer of the Journal of Nuclear Materials Award and the ANS Literature Award. And in 2015, he won the TMS Early Career Faculty Fellow Award, the AIME Robert Lansing Hardy Award. And this year at TMS, he was also the recipient of the prestigious Bramcom Medal. And Professor Hosemann is also known for his dedication to teaching and education. For example, he leads the UC Berkeley blade smithing team, which won the title of the best example of the traditional blade and the commendation beauty for UC Berkeley. And he is also the lead faculty for the Castle Solar Car Racing team, which won the American Solar Challenge for Berkeley a few years ago in 2017. And with that, please join me in warmly welcome Professor Hosemann to give his talk today.
Thank you, thank you. Apparently, I'm not having the word for how to operate my computer, but I'm gonna figure that out some way. Okay, so thank you for the nice welcome. And it's a great pleasure and honor to speak here. I will try to do this. This meeting is being guided. Okay, so. Get a little bit quicker since we lost just a few minutes to get this here sorted out. Okay. So this is the title of my talk. I try to keep it a little bit general, from material selection to deployment, as well as synergies and differences between radiation effects of different kinds on the performance of materials. No, this doesn't work. Ah, there we go. So outline, I guess, I talk two slides about the UC Berkeley's Nuclear Engineering Department and the UCB's Nuclear Materials Research, and then have examples of material selection and additive manufacturing, and then I'll talk about displacement damage and helium effects in materials. I guess it's a different button. So the Nuclear Engineering Department in Berkeley has this our faculty. We cover all areas of nuclear engineering, anything from thermohydraulics to neutronics to reactor design, and as well, of course, as materials. And so today we are talking about materials research in this session. And so as today I met with many faculty of mechanical engineering, nuclear engineering, as well as material science today. So it was really all comprehensive day and meeting. What we do in the nuclear materials section is two things really. We look obviously at materials in nuclear applications, but over the years we learned that what we learned from nuclear application has a lot of implication to non-nuclear things as well. So be it in the nuclear world, we work on materials for conventional reactors as well as advanced reactors. But the material really doesn't care that much. We know how it's used. And many lessons learned also go to non-nuclear applications, including composites for aircraft engines, since we have the same composites or similar composites of nuclear applications. Coatings for tooling are the same coatings people consider for cladding, and so on and so forth. So, and even plasma research you find in fusion actually finds application in semiconductor applications just the same. So therefore, for us, it's really the materials are being extreme issues in extreme application being the issue. And so harsh environments in the associated materials, in the materials challenges need to be addressed. Essentially, we say that every engineering design can only be as good as the material it's made out of. If you're a mechanical engineer and you don't have the right material to build it out of, your design will stay where you put it in the first place, which is on a computer or on paper, and it will never be realized. So you have to have the material to do that. In my research team, we look at mechanical properties, environmental degradation, as well as fabrication and alloy development of materials. And so actually, I'm going to talk a little bit about this first, because particularly here in mechanical engineering, there may be some interesting takeaway things. But we also then look at changes due to temperature and radiation, mostly in regards to mechanical properties. I'm not going to talk about corrosion today, but if anybody is interested, we can talk about corrosion as well. So we could talk about these two aspects. That's a research group before COVID. Looks a little different today. I probably should take a new picture, but it's about similar number of people, but different folks. Many of them, of course, are different now. Okay, so first chapter, so to speak, is materials engineering material selection for nuclear engineering applications. What's other chapter? So if you're a mechanical engineer, you start with your design, and you come up with a set of criteria: temperature, stiffness, whatever is your requirement for your design, and you assign it a materials property, it'd be creep property, strength, what have you, elastic property. And if you're a mechanical engineer who is materials inclined, you will learn that that then you can go to ASPE maps and select something of your liking that you think is appropriate for your application. If you do that and you plot interesting properties, what you find is many properties are related to each other. So for example, melting temperature and elastic modulus are related to each other, and there are some trends along those lines, right? So higher melting temperature usually means high elastic modulus, etc. And that's not really a secret. But what is interesting then, if you're throwing the nuclear application, then you'll start to see that the relationships, that the intuitive relationship between these properties go away. So it's the same plot of various different compounds, and the size of the sphere now represents the nuclear cross-section. And so you can see there's no real trend anymore. So the modulus and melting temperature still have a trend, but the nuclear property has no trend associated with any of the other ones. So that makes it a little harder to do your material selection process. And so if you think about it in your application, particular nuclear, usually you design for mechanical property, you design for some chemical property, be it corrosion, you may design for physical property, a density, or something like that, the thermal conductivity maybe in reactors. And now you have to design for a nuclear property, which keeps your design space very small. And so you have a very limited design space in nuclear application, which fulfills all these requirements. Now, that leads to the question, can you overcome this by maybe some creative engineering or creative manufacturing in some way? And so as a first example, I want to show you it's not that new anymore, obviously. As you can see, we started doing this in 2016, so that's actually quite a while ago. But we look at 3D functional graded materials. So can you do 3D printing by changing the composition and the property at the same time? What I mean by that is, so we borrowed this a little bit from welding, as most 3D printing, right? So you have alloy 1 and alloy 2. And usually people make these dissimilar welds by building what's called a black and white weld, where you build up your transition. But can you do the same thing in 3D printing? So here's a design of some part conventionally. Here's maybe a 3D printed version of this. But can you assign different materials and different properties to different parts of your part? And can you create, instead of 3D structures, maybe 4D structures by changing this material? And of course you can, right? And so I'm going to show you a couple of examples of that. But we do that is laser 3D printing, where you have a powder feed and a laser, and you melt the powder as it comes on, and you build layer by layer. And can you change the composition along the way? Now, of course, your process parameters change, your materials powder changes, the chemistry changes, the geometry may change, the laser parameters may change. You have a lot of changes along the way. And so you have to really figure out how to do that in this instance. Here's a survey, and obviously I don't expect anybody to read this. It's from a review paper last year, where we plotted what have people done in the literature. So people did, austenitic stainless steel to titanium, I believe, austenitic steel to austenitic steel, and so on. So it's all kinds of different materials plotted against all kinds of other different materials, and looking at what gradients people produced over the years and where the pitfalls are. So all these acronyms in here go and say that you have maybe poor solubility, which may lead to embrittlement, or you have a very different thermal expansion coefficient, which may lead to cracking, and so on. So all these different materials combination have all their challenges. Now, in our research, we focused only on, not all of them, obviously, but on 5, and I really just show you one in the interest of time. So I'm going to show you a martensitic precipitate hardened material to an austenitic steel. The point of this is mar-aging steel is a very, very strong heat treatable material with 2000 megapascal yield strength or something like that. And stainless steel is corrosion resistant, but it's pretty weak. So can you make a transition from one to another without too much trouble and use it for your design? In fact, that particular project was inspired by JPL, as you saw earlier on the logo, and they were interested in doing something like that for space vehicles, because there's very limited space. You can't make too many connections. That's very interesting to see if you can grade something. So we plotted mar-aging steel C300 to 316 and did layer by layer a gradual change of the composition. And as you can see, it's 100 some layers. And you change the composition along the line. The powders were pre-mixed, and so you change the composition gradually. Okay, so far so good. It is important to know, however, what the phase diagram looks like when you do that, because you end up with multiple phases potentially. So we plot here the iron, chromium, nickel phase diagram, and we want to go from a 316 stainless steel to a mar-aging steel. And we chose a straight line. Of course, you could choose other directions. You could increase, the nickel content and reduce it again, do some other path if you find that there's some intermetallics on the way. In the titanium world, that's sometimes what people want to do. They want to avoid the intermetallics, but in this instance, it's not necessary. However, you still join now a very different FCC material, the BCC material, something with 500 something megapascal strength to 2000 megapascal strength, and very different thermal expansion. So it's a reasonably different material. And so when we print these things layer by layer, afterwards we do a cross section here. And we look at the EBSD in this instance. Blue is BCC, red is FCC. Those are the orientations. And as one may expect, if you go from a BCC to an FCC material, you get a mixture of the two, and somehow in a gradual way. When we now pick a specific location here, we can then go and plot the hardness. Now we may expect that because you have a continuous mixture of FCC, BCC, that the hardness gradually changes as well. Well, it turns out it doesn't. The hardness actually changes very abruptly. And exactly at one compositional changed layer, you have a steep drop in hardness. And it's not a gradual thing like the mixture may suggest. And of course, it's heat treatable mar-aging steel. So, when you heat treat it, it pops up quite a bit in hardness to an aged version. And so that's what we end up here between us. Now, so that's interesting. Why do you see a difference here, a gradual change, but not a gradual change in the hardness at all? Now, when we etch these microstructures, again, here's this FCC BCC mixture. This minor segregation causing the slight difference between FCC and BCC. But only some of them etch, as you can see, and some of them don't. Not all of them etch at the same rate. And when you then do a hardness, you can see this is the soft region, large imprint, hard region, small imprint. So where it etches, it's harder than where it doesn't etch for some reason. And so in the TEM, however, we did see that in the hard region, we see a lot of intermetallic precipitates in this region, but not so much here. So what seems to have happen is that in the hard region, we form a lot of intermetallic precipitates that, however, uses some of the alloying elements, therefore it doesn't contribute to the corrosion resistance and the etching, allows it to etch, versus in the soft region, we do not form those intermetallics, and therefore it also doesn't etch because it stays in solution. And so that's one example where we, when you set off to do a gradient, you have to really be careful that the gradient is indeed a gradient and not a sudden transition in some way. So that's something to keep in mind when you do this is grading. Okay, second example on 3D printing is also a gradient, but in this instance, it's a structural gradient. We look at P91 or T91 ferritic martensitic steel. And when you build something, you have a bottom part, some in the middle part, and top parts, you build layer by layer, as we showed earlier in this cartoon. This is the EBSD to these. Doesn't look terrible different. Maybe this has larger regions and this may have smaller regions and something. But there's a lot of stuff happening within these regions. They're not particularly homogeneous. There's a lot of structure in these things. So let's look at that. Professor Deborah from Penn State actually did a beautiful modeling where he let the laser beam go across, calculates the thermal, the temperature as a function for the laser beam is, and then calculates the thermal history layer by layer. Remember, you do layer by layer. So the next layer treats the layer underneath, and the next layer treats the two layer underneath, and so on and so forth. And they see different thermal history. And so now you can, because you have different thermal history, you also have different heat treatments for these heat treatable steels. And therefore one would expect a gradient of some sort with different heat treatments on top layer to bottom layer to change the property. And so this is the product, so layer by layer. And what's interesting, if you look at the top layer, the bottom layer, we see a very different yield stress, ultimate tensile stress and yield stress change as a function of which layer we're looking at when you do tensile tests along the way. Again, the top one has only seen one heat treatment, maybe two, and the bottom ones have seen many, many heat treatments. Today, everything so that's it. So the question then is, okay, what does the microstructure look like? And Shmuel, a postdoc working with us, is really good in EBSD. So he records all these different layers, the EBSD microstructures, uses them to calculate packet sizes and grain sizes and microstructural features from the EBSD. Calculates the cluster densities, the lath dimensions, all these things, and can reconstruct what this microstructure looks like when you actually deconstruct it in grain sizes. And what you can also get out of this is the geometrical necessary dislocations in these microstructures. And what we see is there's a delta ferrite grain or phase here at the martensitic phase. And all the red in here is the highlighted dislocations. Now, what you do plot is the dislocation density as a function of distance along a build direction, but also the tested yield stress. And of course, if you have a higher dislocation density, you get a little bit higher yield stress and the other. Now, of course, you have to consider how much delta ferrite phase you have and what the rest of your microstructure looks like. And if somebody wants to see the rest of all this put together, I can obviously show you this later, but it's really remarkable that you can see as a function of build layer, you can change the microstructure, get different properties, and you control it, do that in a targeted fashion. All right, with this, I would like to stop with the additive components and talk a little bit about radiation effects in materials and mechanical properties. And I'm rushing for people who came later because we lost 15 minutes at the beginning because we had computer issues. So, all right. So we looked at, let's look at materials in the nuclear environment. Again, remember what we said earlier, that this is extreme environments is this coupled avenue. It's not just radiation, it's mechanical, temperature, and these things. So since here, maybe we want to briefly talk about the background on radiation damage, what can happen when radiation hits material. Well, one thing you can create is you can cause displacement damage. And here's one of the very first depictions here of what that may look like. In the meantime, we got a better understanding of what it actually looks like, but nevertheless, it's still illustrative. Your energetic particle comes in, displaces your atoms, and then you create knock-on cascades, which displaces all the other atoms around. Of course, most of those atoms jump back at the end of the day, and you have a sort of Hilbert lattice. But you had these atoms being displaced, and therefore our dose we characterize in nuclear materials is displacements per atom, is the dose unit. So in 1 dPa, 1 displacement per atom means that every atom on average has been displaced 1 time from its original lattice site. But you can also have transmutation products. So you can have your atom being transmutated into other elements, being helium or other things. And so that's also something to consider. Now, the displacement damage leads to dislocation loops, maybe voids, maybe segregations, precipitate forming, these kind of features. Versus transmutation products or gaseous products oftentimes can lead to, in the fusion world, to fuzz formation on the surface, or helium bubbles building up in the material, or blisters forming underneath the surface. So those are very different phenomena that can happen, right? Now, the result of this is that your material may swell, so you can have a volume change before radiation, after radiation, tens of percentages can happen. Of course, if you have a component, imagine a screw or a bolt that changes its length and its diameter just dramatically. That's awful. You can have cracking. Here's actually a bolt from a reactor that's caused by embrittlement. Or here's a tube, a stainless steel tube that they have just held in a vise just to hold it in the hot cell, but then just by holding it, it actually fractured. It's that fragile sometimes. So one has to be rather careful. And of course, the resulting data is where you have a shift in ductile to brittle transition temperature. That can be problematic, or increase in yield strength, but a decrease in uniform and total elongation, which of course means this material behaves rather brittle. So those are the effects of this. And the cause of this, as I mentioned, are loops, voids, stacking full tetrahedrons, precipitates. Sometimes you can also get the dissolution of precipitates. So when you have strengthening phases like gamma prime, gamma double prime phases, when they get irradiated, they can disappear under dose. So you can actually shoot them back in solution. So you can actually have both. You can have the formation of precipitates as well as the dissolution of precipitates. And helium bubbles. And for the remainder of this talk, I would like to separate it in maybe defects that may be dissolved by mechanical deformation and defects that usually won't be dissolved by mechanical deformation. So stacking full tetrahedron, if a dislocation comes or a dislocation loop is there and a dislocation comes, they can be absorbed by those. And that leads to different mechanical performance than, for example, let's say helium bubbles, which may change their structure, but they won't actually get dissolved. Now, when we have our material, we want to irradiate it. Usually we have 2 ways to do this. We can either have a reactive radiation, which leads to macroscopic dot bones and samples and what have you. However, they're going to be highly radioactive, and therefore we would like to do smaller samples to keep it safer. But we also can do ion beam radiations. You have, of course, one of the world's premier ion beam facilities here. I'm well familiar with this. The ion beam radiation, but then your penetration depth is limited, so you have to also go to small scale mechanical testing, because otherwise you can't test the material in that volume. In either one of those applications, small scale mechanical testing can be useful for both, and so I'm going to show you examples of small scale mechanical test data of these phenomena we just discussed. So as the first case, I would like to talk about radiation damage on 3 or 4 stainless steel. In fact, that sample has been irradiated here in Michigan and was studied in Berkeley. So it was irradiated 2 MeV protons, penetrate about 20 microns deep into the material. Here's the dose profile shown, and where the protons end up at the end. And so 20 microns is all the material you have to work with. If you look at, so the beam came from this direction, this is how deep it penetrated. And we looked for a large grain, which can accommodate many, many mechanical test samples. So each test pillar in this instance is in the same grain as its neighbor. So orientation doesn't matter. It doesn't play much of a role in this instance. So and the nice thing also is if you put your mechanical test samples beyond penetration here, then it's unirradiated, and so you can sample different doses along the way. That's what that looks like in real life, but that's not really all that exciting. So let's look at these pillars. This is obviously a little bit older data. What we look at is the stress strain curves on the left side. Here, stress strain of these pillars, and this is unirradiated, irradiated, and this is irradiated, but at the stopping peak, right where the peak is, around there. And so the top movie here shows you a pillar, unirradiated. What we see is nothing too exciting. We just squish that thing. It gets a little bit bigger and a little bit shorter. But the irradiated version is interesting. There we see actually a white line popping up here somewhere and another white line popping up there somewhere. And we see that the geometry doesn't change much as a whole, but with the sudden deformation, there was a little sudden jump, and now this white line is increasing, and there's another one popping up. So all the deformation actually only happens at these two locations in this instance. The rest of the pillar doesn't deform much. And we can relate these load drops, these events, to load drops in the stress strain curve. What happens is all the deformation happens at very localized regions. And when this happens, then it's kind of, so you see the load drops because it's under stress. And when the deformation goes, it goes, and so it overreacts, and so you can, when you push somebody, pushes back, and then you kind of do this opposite motion. It's a slight failure in the feedback loop. That's why you have this load drop. So we look at not irradiated. In the not irradiated case, we see many slips, all parallel, of course, since it's in the same crystal. But in the 10 dPa region, maybe one, maybe two of these things. And all the deformation happens only there. It's one clear shear. In the stopping peak region, we see a little bit of both, but our stopping peak is 1 micron wide, and the rest of the pillar is like 2-3 microns wide. So it's it mixes both. Unfortunately, it's not that localized. So when we look at the load drops, what we actually look at is each data point, and when an event occurs, the spacing between the data recorded changes a little bit. So you can use it as a go point. At that point, you have a plastic deformation. And then you map out or calculate the area underneath the force displacement curve, which tells you how much energy went into this particular event. Force over distance is the energy associated with the load drop in my stress strain curve. And so then I use this energy and put it in correlation to the pile stress, which is the stress it takes to drive a dislocation through the lattice. And then I take my pile stress and multiply essentially with what is the dimension of my pillar and the surface energy term, because you create new surface at that point. And that's the energy it should take me to create that load drop. So this is what I measure, and this is what it should be. And when I divide one versus the other, then I can calculate how many dislocations take part in that event, because one dislocation causes yay much deformation. And so one total energy divided over the energy of one dislocation gives me the number of dislocations. And so the number of dislocations times Berger's vector should give me the slip step height. And I do that, then I calculate that in the non-irradiated material, I see a slip step height of maybe 50 nanometers, maybe 100 nanometers, depending which one you pick of. The load drops, they're a little bit different. But in the irradiated case, I see 800 or 900 nanometer slip step heights, which is in correlation with what we see here in our SEM curve. So that's consistent. Now, why does that happen? Well, it's well known that this is the TEM of one of those deformed pillars. There's one of these channels where the deformation happened. Well, the radiation effects in this instance are maybe very small loops or stacking fold tetrahedrons. And when I have a dislocation passing through there, these defects get absorbed in the mobile dislocation, which means the next dislocation is going to have a little bit of an easier time passing through the same area. And so the 5th or 10th dislocation has very few radiation damage. That's why all the plasticity is localized in this channel. This is not particularly new, unfortunately. This has been shown in the reactor-rated materials that deform these, in deformed reactor-rated materials that deform these channels with no defects in them. And that's because these dislocations clean out the area and therefore leave these traces behind. However, any subsequent deformation will be in the same channel. And therefore, all the plasticity happens in this very narrow gap, which then leads to these low drops. You can do the same thing in tension. So this is stress strain. Again, tension, unurated, however, in different orientations. This is grain 2 and this is grain 1. So the different orientations not corrected for Schmidt factor. But you can do the same thing in irradiated and unirradiated look different. We have a reduction in total elongation in the tension case, just the same way as one would expect of irradiated material in this instance as well. So tension compression does the same thing, and we see that happening. Okay, another example of this is something last year where we used these pillars again, but this time we actually look at ordered structures. So we look at a nickel chromium alloy, and nickel chromium, when it's aged, form these long-range ordered features, precipitates, if you will, but they're not real, they're long-range ordered structures. So you have chromium nickel being on specific orders. And when we did this test, what was interesting when we observed this, you see mostly, again, slipping taking place. But in one orientation, in fact, in the one orientation, we saw something different, which is not slipping. So in this movie, I would like you to pay attention to a black band popping up at some point. Or not. There's a black, oh, there we go. There's a black band here popping up at some point. I don't know if you can see it or not, but and it just keeps growing. So there's a first event, and then there's this dark band here, and that band keeps just widening. It's actually this band here. I think it's the same color, if I'm not mistaken. And that's not slipping, that's twinning in that instance, right? So the material actually started to twin rather than slip. But it only happened in this one orientation, interestingly. So if you do it in all the other orientations, it keeps slipping, except in the one orientation. Now, it turns out that there's an orientation relationship between the long-range ordered feature and the host matrix. And in almost in all orientations, you can do that slipping and not change the stacking order, except if you apply the stress in one orientation, then you would have to create an anti-phase boundary. That costs you a lot of energy. In that instance, the material rather starts twinning than slipping. And so your deformation mechanism actually changes in that instance. So in that instance, you can dial in what deformation mechanism you want, depending which orientation you push it, which is kind of interesting. All right. Of course, we do all this in a micro scale. Now let's do this at the slightly larger length scale, because we really, at the end of the day, we want to get bulk properties for our reactor. And one challenge we have is people have been doing tensile testing using focused ion beam machining for the last 10, 15 some years. And our reactor, however, is in the millimeter length. And what's missing is sort of this stuff in between, sort of the 100-ish tens of microns length scale. Because the question is, how does your nanomechanical performance relate to your macro performance? What is that relationship? And the truth is, it's really hard to get to that, because who can make a 50 micron diameter dot ball, right? That's the hardest length scale to make anything. It's too big for fibbing and too small for anything else. So we're really interested in finding out what is this relationship between yield stress and the nanoscale and the macro scale. And we know it's something in here. It's something like that. I don't know what it is, but it's something like that. And so we're looking at that. In order to access this, we started to look at other ways of making these microstructures. So machining, of course, and EDMing is conventional. FIB we already discussed. Femtosecond laser machining is something we got interested in like 3-some years ago. And that has been very fruitful, really. In Berkeley, we got this Spirit 1 laser with a bunch of optics in there. It shoots in, optics come from there. And think of it as a CNC machine, but using a laser rather than a tool. And it's actually pretty cool because we can put the sample in this device here. The sample is inside here. And you shoot through a glass. So you've got a glass window shoot through. So all your radioactive debris is captured in that chamber. So I can have beryllium, toxic material, radioactive material, anything really. Nobody cares that much because it doesn't ever leave my vacuum chamber. And that becomes a consumable and my piece is ready to go. Jonathan Giga from Los Alamos and I studied a little bit what's the effect of this. So here's different pillars cut with this laser and looks pretty nice. They do sometimes require a little bit cleanup. As you can see, the surfaces can be rough. Now, this is from 3 years ago or so. So by now, we got much better in this. These were really the first pillars we made. But the nice thing is we don't see, any kind of recrystallization. It's all one grain. It's stayed that way and didn't really change too much. And and if anybody wants to know the data, the stress strain data to these things, of course, we can discuss further, but I want to show you what the pillars look like. And recently, we started to make more tensile tests. So this is SSJ2 tensile geometry. So they are 1.2 millimeters wide. They're the standard nuclear reactor tensile test samples. But now we use these very same ones and cut small samples in those bigger guys to really try to understand what's the relationship between sample dimension and property, and that they're not independent from each other. But that way we can guarantee it's the exact same material, right? Because it was cut in the same piece. So, and also you can do, many of these dot bones on one, what do you call a coupon, if you will, like this, and then pull one after another. Andy Miner just bought recently an automated tensile tester, so you can literally go there, grab one, pull, and you come back and that sort of stuff. And what I'm really proud of is something Jason, my student, did. He was able to actually make round geometries. So we put a lathe in the laser, so it's rotating, and now you have a laser lathe, which is non-contact machining, non-physical contact machining. On any material really, and gets you pretty good geometries. This was again from 2 years ago, and now we're able to make those about half that size. And also we just did a test. I should have put that in, but did EBSD of the surface as is. So you can actually get an EBSD signal of that without fibbing if you get the parameters right. So with that, we are able to now test. For example, sample thickness versus yield strength, because we really want to know what that relationship looks like in unirradiated case, and then irradiated. This is actually a 30 MeV deuteron, I think, irradiated samples. And so yield strength versus sample thickness plotted, or ultimate tensile stress versus sample thickness, and those are basically those samples here, where they have different thicknesses and the same XY dimension, and we cut them down thinner and thinner and thinner, and try to understand that relationship. How much can I go this way and still get valid data out of it? And what we can see that 30 MeV deuterons, fraction of a dPa, actually did already change the property in this instance, right? So the yield stress is higher in the ion beam irradiated material, but at the same dimension. So that's where it's heading at this point. Okay, and the last chapter I want to talk about is helium implantation. As I mentioned earlier, talk about displacement damage, but there's also transmutation damage. And transmutation damage, you create helium in materials and on surfaces. And here it is, for example, blister. The way we do this is we have a helium ion beam microscope, and that implants helium in like 10 by 10 or so microns. You scan, you raster like an EFIB or like an SEM, and then after you have on the same grain in the same region, and then you watch swelling, you do AFM, and you watch the swelling, you do non-indentation, watch the hardness, you do TEM, watch the TEM, and get all that out of a 10 by 10 sort of micron region. Very effective to get many doses in the exact same sample. This is what the dose profile looks like if you do 25 keV helium, like in this instance, not of course accounting for diffusion. Diffusion smoothens that out some more. But we usually do between 1 × 10 to the 17 to 1 × 10 to the 18 helium ions per square centimeter. So pretty hefty dose. That leads you to about 40 or 50 dPa of displacement damage. So let's see what that looks like. So here's 1 × 10 to the 17 helium ions, 5, 7, 1 × 10 to the 18 in copper. And we see, of course, with the AFM, the rising of the surface. And at high dose, like in this instance, we see these features popping up, which are actually blisters. We're going to see in a second. And so, yeah, so one of those features actually looks something like that. So these are like little domes popping up. Now, interesting features to note, they actually have all this X shape, and then they have a second X here. They have 2 X's in there. Now, the dark X comes from the fact that this was a single crystal copper, and when it bends it, now you end up getting channeling contrast, specific crystallographic directions. And so that's what we see here. These, however, they're probably slips from the surface because it had to undergo some plastic deformation. When we plot now height versus distance, we can measure height change as a function of distance, and then plot that as a, where's my, oh, it's coming right here. And then plot swelling as a function of dose in a second. And then in the TEM, what we see is beautiful helium bubbles building up in the material. In this instance, we see an ordered structure of helium bubbles. We see at this dose, the fast Fourier transformation shows us that peaks. So there's an order to these things. But if you go too high in dose, you lose that order, and it looks a little bit more like bubble bath. And so you have just too much helium gas in that instance. And so we can now plot swelling as a function of dose. And so in copper, single crystal copper or polycrystalline copper, our fields are so small that they're always more or less single crystals. So it really doesn't change a whole lot. And so we look at that swelling rate as a function of dose. But we also compare the T. So the other thing we compared is we count the helium bubbles and then say, okay, the helium bubbles are the empty space. And from the TEM, I calculate that we should get 97 nanometer height increase or 39 in this dose. And from the AFM, I measure 91 and 33. Okay, so B, right? But you can account for the empty space. That's what I'm saying. So that the TEM image agrees with the AFM. Well, that's good. But the question then is, are my bubbles overpressurized or not? And what's the pressure in these things? And so you could consider, Van der Waals gas law and say, okay, I know how much helium I pump in this thing. The helium must be still there. I know the size of my cavities and how much pressure should be in the cavities by doing so. And what we learned by this, that the sample with 5 × 10 to the 17, for example, should contain actually this much dose based on the microstructure. So we can contain a lot more helium than we actually put in our material. And so to account for the bubble size, if the bubbles would be in equilibrium. Same is true for 1 × 10 to the 18 should contain this much helium. So that means our bubbles are under pressurized. They actually have a lower pressure than they can accommodate based on it. Well, why is this? Because at the same time we're pumping all the helium, we're also pumping in 50 dPa of displacement damage. and we create a lot of vacancies and interstices at that point. And so a lot of that cavity space is actually attributed, therefore, to the vacancies rather than it is just the helium itself. So that was kind of interesting to do. Now the non-indentation is also interesting. So we do indentation, displacement versus elastic modulus, so depth versus modulus at different doses, and hardness versus depth as well. Now, as more dose we pump in there, so this is unirradiated or control, I guess, these things, and this is 1 times 10 to the 18. What we see is the elastic property drastically reduces. Well, it's not hard to imagine because now you have all this empty space. It's more like foam-like almost with this many cavities. And so your elastic property is reduced. However, the hardness, this is hardness unirradiated, but as you radiate, hardness goes up. But then at higher and higher dose, hardness comes down again. Well, why is that? Well, first it goes up because even though it creates empty space, there are dislocation obstacles and therefore they're hardening. But at some point, you have more empty space than you have solid space, and therefore it becomes weaker as a whole structure at the end because it behaves more like a foam. But interestingly, it never reaches quite the level of unirradiated. So it always stays above, even with this much helium in it. So you do have still some remaining hardening at the end of the day. And last but not least, I was going to talk about these blisters for a second. So we see these little bumps, the cross section of these bumps. This, however, is not copper, so I apologize for that. This is tungsten. I don't have quite the same nice picture for copper, unfortunately. But for tungsten, you see these beautiful same blisters, and you see these cracks here forming, and you see lots of small cracks too. But in TEM, if you look at the helium bubbles, the small ones, you actually start seeing those things connect. And tungsten is a reasonable brittle material. So what happens is these helium bubbles start connecting to each other and they create a crack. At some point, you will have a critical crack. And what drives the expansion is the fact that they're gas filled. And so as the gas, the bubbles accumulate, the gas will expand. Therefore, they have the surface to volume ratio is different, and they will lead to that expansion, and that's the driving of this blistering effect. You can see very nicely how the helium bubbles start connecting and ultimately form these initial critical cracks. And it can be so bad that the whole blisters just simply pop out. We didn't do anything to those. They just were irradiated and they just popped out by themselves. Kind of like that. So that's pretty nice. And even the tungsten, you can see has this black across as well. So again, single crystal as well. All right. And something we did recently is then look at these blisters and see what happens when you have a blister here and then you indent on those. What is that performance of those? So when you now think of a balloon and you start squeezing it, right? And can you say something about the pressure, or can you say something about what the material does to it? Interestingly, first when you indent, you can see where the indent was. A couple of things to note. First of all, it pops back out. So that's good, I guess. So it's like one of those clicker thingies you have, when you click, 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 and then it comes back. The other thing is that your bubble actually changed, or blister changed shape. The shape afterwards is bigger than this one, right? They're not the same shape any longer. And then when we look at the stress strain curve, which is interesting, that if you go to low loads, you can actually repeat it a few times and relatively often. Let's just poke it very low load. But at some point, you hit the point of no return. So we load it, hit the point of no return, unload, reload, and then you increase. This is pure elastic because it comes back a few times, but then it changes slope. So there's some plasticity. You have the expansion of this in a lateral way. You apply pressure, your balloon squeezes that way. And at some point, you will hit, of course, it reach a point of no return, but it pressures all the way through. We have closed the gap, right? Once you close the gap completely, then the force goes up all the way because now you have solid to solid contact. There's no more gap in between. When you unload, you first have elastic reload, but it does pop back out, interestingly. So this is something relatively recent, and to be fair, I don't fully understand it at this point, but it's a fun thing to do. And we want to learn for example, what I really want to learn is what can we derive from this, the fracture propagation at that interface. Can I learn what is my fracture toughness by using the gas in that blister to drive the crack propagation? So that's the aim, but I'm not there yet. So that's where we want to take this. So with this, I'm a little bit over time. I apologize for this earlier snafu with the computer. But give you a brief introduction to nuclear materials at UC Berkeley. We talked about 3D printing, changing properties along prints, either compositionally or microstructurally. Then we talked about displacement damage and what that means for something which doesn't have precipitates, like 3 or 4 stainless steel with its own loops and stacking full tetrahedrons, or what that means for precipitate materials, that they can either dissolve or not dissolve and change deformation mechanisms. And subsequently, we talked about helium implantation using helium ion beam microscope, what that means for helium bubbles, that they change my mechanical properties. I didn't show the pillar version of this. It's the same as the other ones. If anybody really wants to see in this time, I can show you that too, but it shows the same thing. So with this, I say thank you for your attention. As in the introduction, we have the CALSO, the competing team to Michigan solar car racer team, right? I'll have to point that out. We're competing against you, and we're doing really well. And we also have a bladesmithing club for the TMS bladesmithing, and that's a lot of fun as well. So thank you for your attention, and take any questions if you have any.
Oh, so we'll have time for questions.
Thank you for your talk. So in your part right there, additive manufacturing part where you showed the 2 phases of materials, can you give us some information about the manufacturing process?
Yeah, sure. I mean, it's all published, right? So it was the machine was from RPM in North Dakota, South Dakota, and they had at the time, this is a few years old. At the time, they had the hoppers, and we changed the powder continuously. If it's not listed on here what the laser power was, I can send it to you. And I'm just trying to look it up what it was. I don't remember on top of my head what laser power was used, but doesn't actually. Well, okay. So an argon atmosphere, 1 kilowatt, and the Yak laser. What the actual power setting was, it's in the experimental section of the paper from 2016, so I don't remember. But either you download it or I send it to you.
Sure. Yeah.
I mean,
yeah. So you showed that nice round sample with the femtosecond laser.
Yeah.
So how does it compare with different shapes? With square versus rectangle, does it matter?
Yeah. So what we found so far, the shape doesn't matter, but the aspect ratio matters. And of course, in a round, at least in the diameter, it's a 1, obviously. But in the flat ones, that's not 1, right? And there, if you exceed, I think that I don't want to tell you the number because I don't know if it's 5 or 7, but something like that. The aspect ratio difference, your deformation mechanism changes dramatically from necking to really a tearing kind of things, because your stress state changes locally, right? So you can actually explain that with the surface stress state of the material. So you really need an aspect ratio of no more than 1 to 3 probably in order to do that. Now that's not even talking about microstructure yet, right? That's just simply the stress state. If you want to, then you have to consider, of course, the grain size and what is the strength. The way I like to say grain size is maybe not the best way, but is the strength. What is the strength determining feature? Maybe here's a good way. The strength determining feature I'm actually after. And that may be sometimes the grains, sometimes it's precipitate, sometimes it's radiation damage, depending what that is. That may change the length scale by which you get bulk properties. So this is from a little while ago, but here's the length scale versus the yield strength, right? This is typical size effect, right? And this comes, of course, from the dislocation density changing during your plastic deformation, right? And if your sample gets smaller and smaller, at some point you have no space for dislocations to be, and therefore it becomes almost ideal strength. And people have shown in whiskers, they get very close to ideal strength. And so it comes down. But then the question is, what's your Schmidt factor? So if the Schmidt factor is different, of course, then you get very different outcomes. But if you have an irradiated material in some other work, it's not shown here necessarily, but you actually see it does this, it stays high. Because in that instance, the strength determining feature is not the grain size or the orientation, it's the radiation effects. If that's the case, then it's just, we just published a work with our colleagues in the UK, Chris Hardy, where we looked at chromium precipitates in copper, and you can very nicely tailor the precipitates density with that system. And you can see that if you tailor it just right, you actually stay pretty much constant all the way. Because if your strength determining feature is very small, then the dislocation density plays no role, because that's not the strength determining mechanism. And so really you have to be always asking, I always ask, what is the property I want to measure? And of course, if you go for grains, then the challenge you have with the Schmidt thing, there's not way around that. But if you have precipitate strengthened material or lattice strengthened material or any of the other things, then you can push this to much slower mixed scales. So I don't know if I answered your question. But I guess we were talking about the laser thing, right? So
aspect ratio is what you say.
yeah.
Is there any particular application or property for which you would recommend doing the round test as opposed to rectangle or square? Like when would you want to take the trouble to make the round?
If I can't make it thin enough,
Okay.
right? So if I can't make my sheet too thin, then it's probably better off making it round. Because the way we make those, right, we polish them, the thinnest you can sort of polish mechanical is like 30 microns, give or take. And that's a little bit of a gamble at that point, right? Not every sample is going to be a success. So in that instance, I would probably, if you want to be smaller than 30 microns or so, then I would probably do it round, because that way I can guarantee it's always 1-to-1, right? Because smaller than that, I can't polish it, right? So that's probably an example. And also, what's your stock look like, right? So many times I don't have a sheet. Many times I just have like toothpicks, right? And I can't make that. So that gives me more flexibility. And really, I think what's the smallest you can make it with hand is probably another way. What I haven't done yet, which I'm very eager to do, and we actually just made about a dozen of those, and want to with the EBSD and tensile them, test them with EBSD on, so to speak, and watch the orientation change on the surface. And if it's round, in theory, at least you could do from different angles. Which when it's square, you have the corner that you only got one side. So you may have a little bit more there. But we are early in that stage, so I don't know, maybe there's some other reasons to do it round versus square. But it's cool that you can. So, do you have any other?
Have you ever compared samples with same composition but the crystalline versus amorphous? Because you have an intermetallic sample, right?
Yeah.
You know that intermetallic is very easy to become amorphous on radiation.
So we actually just started doing that with a bulk metallic glass, and did some indentation. We haven't published it, and it's pretty new. There's one poster who came from Jan Schroeder's group in Yale, and there's a lot of bulk metallic glass. And you got this beautiful bulk metallic glasses, and they're very radiated, helium implanted with the same method, and then indented. And it behaves very different from the crystalline version, very, very different. In fact, what we see is you can see in bulk metallic glasses, you get these slip traces, right? The shear traces, and you can see those. And what happens is the helium bubbles actually line up where those shear traces happen, and they grow in that way. Beautiful thing. And the hypothesis there is it looks something like this. Helium implantation, we did an indent, for example, and what you see is helium bubbles sort of lining up all the way in that shear zone, which is very different from the crystalline version, right? Because you're not going to see that in the crystalline version at all. And the reason is we think it happens is that the hypothesis why you have these localized shear bands in BMGs is because you have a heat development usually in the deformation. People say you can get quite high temperature, and that thought is that maybe that makes the bubbles grow locally. That's why they line up that way, these zones. But I don't know, it's very new, and we haven't really done too much other than the experiment. So, but yeah, and then of course you can do heat treated, right? And then you get it crystalline and do the other way. We did it also the other way around in silicon. So in silicon, we did single crystal silicon and then helium implant that. And first you see amorphization, but then you see more and more helium bubbles building up subsequently, right? And ultimately you get a cleavage at some point, right? So in that instance, you can't, unfortunately, you can't go quite, you can't do the one-on-one comparison because you always get amorphization. So you can't do helium without the amorphization. But that was also quite fascinating to really see. In that instance, when we put in different doses, we saw the amorphization happen here, and then that amorphing band keeps expanding until the whole thing is amorphous. And you see swelling due to the amorphization about 7%. And then when something more implantation, then of course you see the bubbles eventually, and then you see more and more swelling. The only thing which was interesting to me is in the amorphous one, we could put in a little bit more helium than in the crystalline one, and somehow we seem to lose helium. And I'm not exactly sure why we lose helium, but we seem to lose it. And I guess the thought is that in an amorphous way, you may have more loss to the surface again. But I don't know for sure, but we do see a little bit of a difference there. So those two experiments we did so far. Yeah.
So to keep up the schedule, because Professor Hosemann will have another meeting with ME department chair right about 3 minutes. So probably we'll have to stop here. So thank you all again coming in person and from Zoom. So let's give another round of applause to Professor Hosemann.